So good morning. This is the PhD defense of Elena Rodionova, and we'll have the presentation first as usual, and then the public question, and then the private questions. And I invite you to start, Elena.
Yeah, thanks, Manfred, for the introduction, and thanks everyone for coming to my PhD defense. So today we will talk about what I was doing during my PhD and how it all fits together. And mostly we will cover robustness of temporal logics in general, and later we will go into applications for planning and control of different cyber-physical systems. And just a small note that if you guys have any questions, I would really appreciate it if you keep the question for the Q&A session. Unless it's something like clarification, something small, then you can go ahead and ask me right away. So a little bit about me. I'm a PhD student here at Penn, George Papa's group. And when I started my PhD, I was working more on different semantics of temporal logics and different formal languages in general. So my research was mostly theoretical. And later I joined multiple projects on planning and control for drones, verification of medical devices, and also safety of autonomous vehicles. So those were applications to some cyber-physical systems. So it got more practical as the time went on. That's why my PhD can be roughly split into two parts. One about mostly theoretical research on formal languages and temporal logics. And the second part is more about how to apply those findings from the theory to applications. That's why I split my today's talk also in those two parts. In the first part, we will cover some basic knowledge of temporal logics and robustness in general for them. I will present what has already been done and what my main contribution is. And in the second part, we will touch upon those applications of different robustnesses for temporal logic for planning and control of different cyber-physical systems. And just such that everyone would understand, when I say applications, we could use this term cyber-physical systems because those are the systems in which a mechanism or an object is controlled by a computer-based algorithm. And those cyber-physical systems, they cover a lot of applications such as safe autonomy, medical devices, drones, manufacturing, and many, many more. So for instance, in my today's talk, I will be talking mostly about drones, but you should understand that those findings that we will see today can be applied to any of those cyber-physical systems. Okay, so if we want to do something good with those systems, for example, if we want to control them, first, what we need to do is we need to find the language in which we're able to specify what those systems are intended to do. And even though language is a great language, it's not precise enough and it's not concise enough to be able to express the missions of those systems. And moreover, those systems have spatial and reactive requirements. So the standard approach to do so, to express their missions, is to use a formal language or to use logic as one of those formal languages. And one specific type of cyber-physical systems that I wanted also to mention here is called time-critical. Those are the systems in which the temporal aspect of the mission is the most important part. So on top of the spatial and reactive objectives, those systems also have a temporal aspect to it. And not meeting some real-time constraints that those systems have might lead to catastrophic consequences. So instead of using just any logic, the standard approach for time-critical systems would be to use the temporal logic instead as the language to express those missions. And one of those temporal logics is called signal temporal logic. It was invented in 2004 by Aded Mahler and Dejan Ničković, who was my co-advisor back in Austria. And you could think about signal temporal logic as the simple extension of propositional or Boolean logic. So we have such operators as and, not, and or, so the standard Boolean operators. And on top of this, we have this ability of expressing temporal behaviors of the system. So we have additional temporal operators, such as until, always, or eventually. And now we're able to express properties that say, for example, something eventually in the future must be happening, or event A must be happening until event B must be happening, etc. And the signal part here says that the satisfaction of the specification is evaluated over real valued time series that could be, for instance, the trajectory of a drone, trajectory of the vehicle, or even multiple agents that participate in this mission. So now, knowing the alphabet of this language, we also need to understand the meaning behind the formulas, and the meaning is called semantics. And the first simplest semantics that we could define is called Boolean semantics, that defines nothing but the satisfaction or violation of the specification. So the Boolean semantics says if the formula is satisfied or if the formula is violated. And here, for instance, if we have the formula that says velocity must always be below the speed limit, you can see that for this specific trajectory, the specification is violated, and for both of those trajectories, the specification is satisfied. The issue with Boolean semantics when we work with real valued signals is that you can see that we lose a lot of information about the signal that we could keep in mind. So for instance, those two trajectories, they satisfy the spec and we don't know anything else. On the other hand, we could actually obtain more information about it because we have those real values from the signal. That's what quantitative semantics does. So the qualitative or the Boolean semantics only defines yes or no answer. Quantitative semantics gives you the real value number about how well the spec is satisfied or violated. And one of the popular and analyzed quantitative semantics is called space robustness of STL. And it defines this property of how well within the space. So you could think about it as how much perturbation in space does the system tolerate without changing its satisfaction. And again, for the same example as we saw before, now we will have, instead of yes or no, the real value that for satisfaction gives the greater number. So for instance, here, the spec is satisfied more robustly. That means that the robustness value is greater than for this middle trajectory. And if the spec was violated, then the value becomes negative. So the logic here is that the negative big numbers are bad, and the greater the positive number, the better or more robust the evaluation of the system is. And here, I don't want you to get lost into details about the formulas. We won't really need them. I just want you to understand how those numbers are obtained. So for both semantics, for Boolean and for space robustness, they both define through recursive definition. So if you have the formula, you first obtain the values for the predicates, for each predicate within the formula, and then you start recursively applying specific rules as here in order to obtain the value for the overall formula. And you can see that those rules are actually the same for both of the semantics, and they use min and max operators. The only difference here comes from the predicates. Okay, so the space robustness basically gives us this amount of perturbation in space that the system can tolerate before something bad happens. And as I also mentioned before, it has been studied widely in the literature from the theoretical point of view and also from practical point of view. It has been used for planning and control and etc. On the other hand, if we thought about possible temporal perturbation, we could also define a temporal robustness that gives us also a real valued number, but analyzes perturbation in the orthogonal direction, not in space, but in time. And even though there is this need for analysis of temporal robustness, especially for time-critical systems, it has only been defined in 2010 by Donzé and Muller, and it has not been analyzed in depth. And moreover, it has never been applied for planning and control in the past. And that's what our main contribution here is. So my main contribution is that we provide this theory behind temporal robustness. We provide the different definitions and the overall theoretical analysis of the meaning of different notions. And in this first part of my talk, I will try to briefly explain at least the meaning of different notions of temporal robustness, that we will see how this can be applied for planning and control. So let's take a look at the following example. We have some specific signal, and in order to evaluate satisfaction or violation of the spec for each time point, what you need to do is, as we already saw, you first need to evaluate the predicates, each predicate within the formula for each time step, and then apply recursive rules depending on how many operators you have. So you could think about them as predicate signals. And when we talk about temporal perturbations, you could think about temporal perturbations as shifting signal to start execution of the trajectory earlier or start later. So you could think about it as shifting trajectories to the left or to the right. But just for the simplicity of the presentation, because the satisfaction depends on the predicates, let's think about it as shifting the predicates themselves in time. So if the trajectory starts execution earlier, we shift predicates to the left. And if the execution starts later, we shift them to the right. And now the question is, how do those shifts influence the satisfaction of the spec? And the easiest way we could shift those predicates is together. And let's assume that we shift them synchronously in time, because that's the simplest case. So let's analyze that first. And that's exactly what the synchronous temporal robustness analyzes. It gives us this bound on the possible amount of synchronous perturbation that in time that the system can tolerate. And because those shifts can be to the left or to the right, we can also analyze the left synchronous robustness or right synchronous robustness. And here I will briefly explain the left. The results can be extended also to the right. So the main result to understand the meaning behind synchronous robustness is as following. If the left synchronous temporal robustness value is some epsilon, then we can shift predicates together or synchronously in time to the left by up to epsilon. So all perturbation in a synchronous manner by up to epsilon will not change the satisfaction of the spec. And moreover, we can also infer that anything greater than epsilon, and in discrete time it would lead to epsilon plus 1, would lead to violation of the spec, to the change of satisfaction. And here I also, so we specified it in English, and we can also specify it in the formal formulas like here to avoid any ambiguity. So this stands for nothing that left temporal robustness for a specific trajectory and for a specific time point equals to epsilon. Then we can infer that for all shift h, that satisfaction, the Boolean satisfaction of the shifted signal to the left is the same as satisfaction for the default signal. And for any shifts by epsilon plus 1, the satisfaction would change. Moreover, note that this theorem works both ways. We can infer the properties of the system from the robustness value, and we can also obtain the robustness value from some experimental data. So it works both ways. Okay, so that was the meaning of the synchronous robustness. And when we talk especially about multi-agent systems, if, for instance, all predicates are defined over individual agents, you could think about it as individual agents starting all earlier or starting all later. When we have those complicated multi-agent systems, sometimes it would be very beneficial to actually have the ability of saying, how does the system respond to perturbations when some of the agents start earlier or some of the agents start later? So that's the difference between synchronous robustness and asynchronous robustness. The asynchronous robustness, like here, is able to determine the behavior of the system when predicates are shifted by individual amount in time. And let's now take a look at how does the property change depending on the synchronous or asynchronous behavior. So even though I don't give you here the precise definitions of those notions because they're a bit too heavy, because asynchronous temporal robustness is a bit more nuanced, the property becomes weaker, and the only thing that we can infer about the asynchronous temporal robustness is that if its value is some specific value epsilon, then we can shift predicates individually in time by up to epsilon. So you should note here two specific details. The first one is that we cannot say what would happen if the amount of perturbation exceeds epsilon. So we cannot infer the second line of the theorem that stays for the synchronous robustness. And we also cannot infer the opposite direction of the statement. So for instance, if we have some experimental data of the performance of the system, we cannot obtain the value of the robustness itself. And here you can see the statement also again in formulas. So the main difference, again, the recap, is that for the asynchronous robustness, we have individual shifts for every predicate within formula. That's why we have here H1, H2, etc., HL. Okay, so that covers the main idea of both of those notions, the synchronous and asynchronous robustness. The first property, in order to understand how they relate to each other, was the soundness property that we proved. So the soundness is this natural and desired property of any robustness function that we would want to have. Remember in the beginning when we saw the images about space robustness, we kind of said that what we want from the robustness is if the value is positive and big, then it means that something good is happening with the system, and then the value is negative, then it's not good. So that's exactly the meaning of the soundness property. So if you can infer the Boolean satisfaction from this real valued robustness, then it's called soundness. And for both notions of temporal robustness, for the synchronous and asynchronous, the soundness holds, meaning if the value is strictly positive, we can guarantee that the specification is satisfied. And if the value is negative, then we can guarantee that the specification is violated. I want to note here that for the value that equals to 0, we cannot guarantee anything. So sometimes the spec can be satisfied, sometimes it can be violated, and more analysis should be done for those corner cases. I also want to mention that soundness property is a very useful property for planning and control when we, for example, will want to maximize the value of robustness instead of solving feasibility problem for the satisfaction of the specification. Okay, so now we know that both of them satisfy soundness property, but how do they relate to each other? So from the meaning that we saw already, it is pretty clear that asynchronous temporal robustness must be upper bounded by the synchronous temporal robustness, Because when we think about it in terms of possible synchronous or asynchronous shifts, well, the synchronous is just the specific type of asynchronous temporal robustness. So from this logic, they are one is upper bounded by another. So if we saw the formulas, how they are defined, it's actually not that straightforward, and we had to prove those theorems first in order to even in order to reason about them. So that was the first result that we showed, that one is upper bounded by another. And moreover, in a lot of simulations, we saw that usually the strict inequality holds. And we started wondering if they're ever the case where the equality happens, because we couldn't find those executions in those scenarios. And later we were able to find specific fragments of signal temporal logic for which both of those notions, the synchronous and asynchronous, are equivalent. So those formulas, those fragments, include negation normal form. So the formulas that have negations only in front of the predicates. And basically the lemma states the following, that if the formula consists only of conjunctions and always operators, and the formula is satisfied, then the asynchronous robustness equals to synchronous. Because of the duality property, kind of the opposite happens here. So if the formula consists only of disjunctions and eventually operators, and the formula is violated, then again, those two values are equal to each other. So that basically concludes the logic behind synchronous and asynchronous robustnesses. But let's now take a look at the following example. We have two predicates and we have some specific formula. We can show that left asynchronous robustness for this specific case equals to 2, and the right asynchronous robustness equals to 2. So using the formulas that we already discussed, we know for sure that the system can tolerate asynchronous perturbations by up to 2 time steps into both directions, to the left or to the right. So both of those executions would lead to still satisfaction of the spec. Because those notions were directional, we actually cannot infer anything about the behavior of the system if some predicates are shifted to the left and some predicates are shifted to the right. So if they shifted in different directions, if those perturbations happen that some agents start earlier and some agents start later, actually that might lead to a violation of the spec. So both of those notions were directional. And even though sometimes it's good to have the information about both of the directions, there was no notion that combines both of them. And just to conclude this overall theoretical analysis, we also defined the combined left and right temporal robustness that combines left and the right possible perturbations. So now what we can say is that if we have this value of combined temporal robustness, now we are able to provide information about perturbations in time into any direction, into executions to the earlier time or executions to the later time. And again, because it is defined through the left and through the right temporal robustness, it is pretty natural to be upper bounded by that value, because if the combined temporal robustness cannot exceed the value of the left or of the right temporal robustness. And for this combined notion, we also showed soundness, because again, it is this desired property that all robustness functions should have. That's why we also show that the soundness property holds. So this concludes the first part of my talk, where I presented the comprehensive theoretical analysis of temporal robustness, what I believe is my main contribution. So we analyzed left-right synchronous asynchronous robustness, and also presented some results about combined left and right robustnesses. So recently we published a paper where we analyzed those notions for stochastic environments, and we kind of opened the door towards the future research, because there is still a lot of open questions about what would be happening with those notions when the system is stochastic and not deterministic. So when we have, instead of just the signal that is given to us, we have the whole distribution. So it would be very beneficial in the future work to continue this line of research and investigate possible executions of, for instance, risk of not satisfying specification in time, etc. And the second possible direction here would also be the combination of the space robustness and temporal robustness. So now we kind of have these two big chunks of theory that evaluates the space robustness, temporal robustness. And I know that there are a lot of works that try to combine them together, for instance, some average geometric robustness, or arithmetic geometric or average robustness. But I would say they still lack this possibility of giving a specific value to the execution that would allow us to have perturbations in both dimensions, in time and in space. So the combination of those two would be something very interesting to look at. Okay, so now we will shift to the applications and how to use the different notions of robustness functions for planning and control. And let's now define the problem itself. So let's assume that we have some cyber-physical system. For instance, we have a drone and we have defined its environment. And we have the specification in mind. So we have the signal temporal logic formula that we want the system to satisfy. So what we want to do here is we want to find the trajectories for the drones or for the overall system such that not only dynamics, so not only kinematical feasibility holds, but also trajectories satisfy the specification. And this all could be stated as an optimization problem where we try to find trajectories that minimize some cost function, the dynamic holds, input state constraint holds, and the spec is satisfied. And after the trajectories are generated, we have the controller that allows us to execute those trajectories already in real time. So instead of solving the previous problem where the trajectory just satisfies the specification, we could reformulate this problem as we want to actually maximize the robustness function. So we want to find the most robust trajectories. And in this case, instead of minimizing the cost function, what we would be doing is we would be maximizing a specifically chosen robustness function with respect to the same dynamic constraints. And also, in order for the system to satisfy the spec, we should require that this robustness function is positive. And due to the soundness property, we would be able to infer the fact that the spec is indeed satisfied. So that's what we are trying to solve here. That is called robust STL control synthesis. And as for the robustness, we could, for instance, maximize the temporal robustness, or we could maximize the space robustness. Because I covered those two, that's how I will split this part as well. So first, we will consider the problem of temporally robust control, and later we will cover also some experiments of the spatially robust control. So let's take a look at this temporally robust STL control synthesis problem. We're trying to maximize the temporal robustness and let it be, for instance, asynchronous temporal robustness with respect to its dynamics, input state constraint, and satisfaction of the spec. This optimization problem is not easy to solve. So the first thing why it is not easy is because the robustness function is not continuous and not smooth because it uses min and max functions. So gradient-based solvers or solvers that use derivatives are out of the picture. They cannot be applied. Moreover, by definition, the temporal robustness uses counting of steps, and therefore even the smooth approximations of min and max functions would not be applicable here. So our solution consists of encoding the overall problem as a mixed integer linear program. And that was one of the big milestones that we overcame when we worked on temporal robustness. So I believe that no one has ever used temporal robustness for control because nobody could implement temporal robustness because of those issues with it being not smooth and inability to apply smooth approximations or gradient-based solvers. So I won't have enough time to go into details about how we implemented it using mixed integer linear program. The only few things that I wanted to mention here is, as I said, the temporal robustness uses counting of time steps. So you could think about it as counting sequential satisfaction of the spec, like here, or counting violation of the spec, like in this case here. So what we did is we invented this idea of counters, of using counters within our implementation that exactly counts sequential steps of satisfaction or violation, and then adjust them based on satisfaction. And at least you can see that the values for the asynchronous temporal robustness will be the same as those counters. But that's all I will cover here about the details, because I don't want you guys to be lost into technicalities. So just one more comment about the implementation. Even though MLP problems are in general NP hard, so obtaining the solution is not guaranteed, we could still analyze the complexity from the point of view of how many binary and continuous variables were introduced. And we also showed that since asynchronous temporal robustness is more nuanced than the synchronous one, it uses more binary and continuous variables. But at least if the horizon is a constant, then the number of binary and continuous variables scale linearly with the number of atomic propositions and the number of operators within the formula phi. So now, having this ability of implementing the overall optimization problem of maximizing the temporal robustness, we were able to perform different experiments and different simulations where we maximize different notions of temporal robustness. So for instance, here we maximized combined asynchronous, left asynchronous, and right asynchronous for a pretty simple, small specification where we have only one drone that needs to reach the goal set A within some specific time bounds and reach the goal B within some specific time bounds. And now we can compare their executions, we obtain their optimal trajectories. And also, just because we build the theory of what those temporal robustness mean, we can actually infer some information about the system based on the values that we obtain. So for instance, here, since we obtain the combined temporal robustness that equals to 4, well, we can for sure say that the left and right temporal robustness must be at least 4, and that's exactly the case when we check those values. And also we know how much of this temporal perturbation can the system tolerate before something bad will happen to the execution. And later we played with much more complicated scenarios where we had multiple drones, where we had nested predicates, nested formulas. Here we have 2 drones surveilling the area, picking up some objects, dropping off some objects. And it was a very big nested formula. So at the end of the day, we will still be able to obtain optimal solutions within seconds or minutes of trying to solve this problem. And we also release this whole implementation as an open source package. So that concludes the temporally robust control synthesis results. And now, because in the beginning of my PhD, when I joined Penn, I actually joined working with Yash Pant, whose PhD was about spatially robust planning for drones. I participated in a lot of projects where we tried to solve the spatially robust STL problem. And here I wanted to cover also some results of this spatially robust control synthesis. So just a small recap about the space robustness. Because it uses min and max operators, the space robustness maximization is also not trivial, because the same reason of the smoothness and not convexity leads to the problem that gradient-based solvers cannot be applied. And MLP solvers could be applied here, and they were actually applied by some Berkeley and Caltech people. But instead of that, what we did is we used the smooth approximation of the min and max functions in order to maximize the robustness. So instead of the max operator itself, we used this approximated form that is differentiable because it uses only exponents and logarithms. And moreover, this approximation is upper bounded by a constant. So we always know how big the error is between the true value and the approximated value. And because of this property, we also know that the space robustness itself, the approximation of it, will be also upper bounded by a constant. That opens up an opportunity of not just maximizing the space robustness that we cannot solve, but maximizing the approximation, maximizing the smooth robustness instead. And instead of just requiring the space robustness to be strictly positive, we could require the approximated smooth robustness to be greater than this constant that we can obtain from the approximation. And because now we can use gradient-based solvers, we were able to solve even bigger problems with the space robustness, where we had multiple agents, we had big horizons of interest within like minutes of executions, we had very big nested formulas, and we were still able to find feasible and optimal solutions within seconds or minutes of running the code. And as you can see here, so all of those are sped up, but we were able to solve very complicated, pretty realistic experiments with drones in a big scale. The small thing that I wanted to note here is this issue with the centralized planning in general. So with the number of agents increasing, we usually require non-collision separation. So we require none of the drones to collide with each other. And therefore, every specification of the mission includes this pairwise collision avoidance constraint. And because of this, with the number of drones increasing, the number of constraints increase drastically. And that really slows down the execution of the solvability of this overall problem. So that's why, on top of the results that I already presented, we also presented an improvement of that work, where instead of solving the overall problem in a centralized manner, we propose independent planning plus collision avoidance on the fly. So what we did is we went from centralized planning to decentralized planning. And here I just wanted to give you the high-level idea of how this can be done. So instead of solving everything for all agents together, what we propose is, if the mission allows us to decouple the specification into small sub-specifications for each agent separately, plan for those specifications using the same optimization problem that we saw before. And then you might obtain trajectories that have collisions. So those trajectories will be obtained much faster, but the collisions might be possible. That's why you need the second step, that is a collision avoidance. So instead of those colliding trajectories, we want to find an updated trajectories that still satisfy those small sub-specifications, individual submissions, but also achieve the minimum separation requirement between the drones. So the distance between the two drones should be greater than some threshold. And what we did is, instead of discretizing the space in general, we discretized the space of actions, and we used the linear-based collision avoidance algorithm. So imagine that you have two colliding trajectories. Now, for each time step of the trajectory, the first step of the process is provide discretized course action for each of the drones. So for instance, it could be as fly above another drone, or fly to the left, or fly to the right of another drone. So it's a very coarse, finite number of discrete actions. And then using those discrete actions that can be obtained by a learning-based algorithm, run an MPC that will already provide smooth trajectories and continuous inputs to both of the trajectories. In this case, the collision can be avoided. And using this methodology that combines learning-based super fast algorithm with MPC on the fly, we were able to provide some experiments on the real drones where initially collided trajectories were resolved. And after we broke too many drones, we decided to shift into simulations. And in simulations, we showed more complicated scenarios of resolving collisions with obstacles, with more sophisticated scenarios. And later, we even generalized this property from 2 drones to as many drones as the system can tolerate. And here, for instance, you can see the constraint unit cube. We started increasing number of drones from 10 to 20 to 30, etc. And we reached 40 drones with an obstacle that managed to avoid the collision using this decentralized way of planning the trajectories for them. So that concludes my second part of the talk, where we presented kind of 2 subparts. The first subpart was about using temporal robustness for planning and control, and also the spatial robustness for planning and control. In space robustness, we consider 2 directions, the centralized and solutions for distributed planning. So one of the possible extensions of this work could be considering temporal robustness in the same way, in the decentralized way. This still hasn't been done. And another possible interesting direction is, as I already mentioned, MLP are in general very hard to solve, so they are NP hard. And that's why implementation of the temporal robustness using something else rather than MLP would be very beneficial. Another possible direction here would be to provide more guarantees about the behavior when we use those learning-based collision avoidance algorithms for spatial robustness, for instance. So, and as to conclude this overall talk, in my thesis proposal, I presented only the left and right temporal robustness, and we also showed the MLP encoding that can be used for planning and control. And as of today, for my final thesis presentation, I presented also a new results on combined temporal robustness, and also showed results of my work on spatially robust planning and also distributed planning. So here's the list of some of the publications that have or have not made into this presentation. And at this point, I would like to acknowledge some of the people who made it all possible. So first of all, I would like to say thank you to my advisor, George, for supporting me, especially when I needed it the most, and for giving me the freedom to do research in the direction that I find interesting. I would like to thank Manfred and Jorges for being members of my committee and for agreeing to serve on my committee, and to Manfred for agreeing to be the chair of the committee and for the support that he provided. I would also like to thank 3 of the best postdocs I had during my PhD, which is Hussam, Lars, and Yash. Without you guys, this all would not be possible. And I would also like to thank my collaborators from Intel, Maria Ignacio, and also Rajiv from UPenn for all the medical devices work that we have done in the past. And I would like to also mention all the places and all the internships that I have done in the past. So I started my PhD back in Austria, and I'm really grateful for this opportunity and for the possibility to even be a PhD student that started from Austria. And later I've been also an intern, and I had amazing internships at General Motors and Intel. And I also participated in the Cybercardia project, and they really gave me an opportunity of exploring different directions and understanding where my interests are. So thank you for that. And of course, I would like to thank all my friends for all the adventures that we went on, for all the sleepless nights that we spent on writing papers. And I hope that you guys see yourself here somewhere in those pictures. So yeah, thank you to those people. And of course, I would like to thank my family. I didn't know how to put my parents in what order, so they contributed equally to this. And I would like to thank my brother, my brothers, Alex and Alexander, and my sister, Elena, my best friend, Galia, and my partner, Aaron, and also my puppy, Pixel, for everything that you've done for me, guys. Yeah, and at this point, I will be happy to take any questions. And Manfred, if you could maybe refresh our memory on how this whole Q&A is going to go.
Yes, thank you very much for this presentation, enlightening presentation. In terms of the question and answer, I would suggest people, I would suggest first you should place some applause in your picture, as people have done already. And then I think in terms of the questions, we'll try, despite the large number of people on the Zoom call, we'll try to have people just start speaking. If we cannot do that, then I will ask for chat inputs, and then I will coordinate the questions. But let me just try to start somebody asking.
Yeah, okay.
It was too clear or intimidatingly clear? Or
I tried.
I have here two people. Amazing job. Any questions from the audience? Okay, if there's nobody asking questions, then I will maybe start with a question. In terms of computation, you mentioned especially at the end the MLP formulation and then a continuous approximation. Is that, as you move on and try to treat larger systems, one issue was the distributed formulation, but in terms of the optimization, is that the direction that you would be trying computationally to get away from the discrete formulation?
Yes, that's for sure one of the directions. So the main issue with the implementation that I see right now, especially for temporal robustness, is scalability. So because it is done in the centralized manner and because we use MLP, it basically very hard to solve for the bigger specifications. And even though the current solvers have all these amazing heuristics, we cannot guarantee anything about the solution. We don't know how fast it's going to be obtained. And that's why one of the directions would be to maybe use something else rather than MLP, something like at least gradient-based solvers. But for now, we don't know how to do it. That's why, at least for the space robustness, we were able to use faster solutions, such as gradient-based. And later, even for those, we were like, okay, it already performs good, but we still wanted to improve on that. And that's why we tried the individual planning rather than centralized. So for the temporal robustness, that for sure would be two main directions that I would take as the future work.
If I can just do a follow-up, have you tried alternative integer formulations? You know, usually this encoding of the logic in terms of the integers, it's not unique. There are different ways of expressing. And as you know, our experience and other experience, that this may have a very big effect on the computation. Have you looked into that and given up?
Well, I have looked into that. I have not given up. We tried, what we did try is instead of MLP, we tried sequential SAT. So imagine that instead of trying to maximize the robustness, you set this robustness to a specific value and you try to solve feasibility. Usually solving feasibility is much faster. So especially in discrete time, that allows us to kind of solve feasibility for a specific value, then change the value, solve feasibility again, change the value, solve feasibility again. So instead of this MLP, we tried sequential SAT solver. In some situations, it performs better. In some situations, it performs worse. I honestly believe that the current heuristics that are within solvers for sure use something like this. That's why maybe this direction is not as beneficial as it could be. What I believe we would benefit from is, I hope that you remember, we discussed with you once that predicates use big M notation. So they use epsilon definition of like feasible sets. And even trying something different rather than big M notation would maybe possibly benefit our implementation. And I did take a look at the paper by Bamparad and you guys, where you discussed at least which of those versions can be beneficial in specific setups. So we tried a couple, but for the current implementation, I presented already the fastest results that we obtained, but we did improve using all those possible ideas, you know, of implementing predicates in a different way, implementing operators in different way, etc.
Thank you. I have nobody raising.
I can ask some questions. Very, very nice presentation, very smooth and easy to follow. I'll start with some kind of question about temporal robust planning. I'm wondering whether when you try to maximize the temporal robustness, for these examples that you have here on the screen, and maybe I can use the annotation to just a second. All right, so let's say why you wouldn't be getting a trajectory like this, right? And then follow here and go right on the boundary, for example. If you don't have, oh, I chose the bad color.
Yeah.
Let me, right, why not go right? Yellow is not good either. Maybe blue. Why not go right on the boundary, right? You don't have anything to push you inside. And maybe even if you have time constraints, let's say if you want to say eventually from time 1 to 5, then effectively the UAV will hit the boundary of the box at time 1 and then follow the box until time 5 and then exit, right? Because that will be the maximally robust with respect to time.
Yeah, so you are correct. Those executions are possible. So what I assume that happening here is the temporal robustness for both of those trajectories will be the same. What I did see from the experiments that I performed is actually in general, this is exactly the trajectories that you would get, the ones that you drawn, where the agent kind of doesn't even go inside the goals. It only follows it on the border. And I mentioned it in my thesis. So for temporal robustness, that's usually what happens. It doesn't go inside. But the space robustness, the opposite happens. It does go inside, but the temporal robustness is usually very close to the border. For this specific execution, I do not really know why it went inside. I assume it has something to do with the dynamics itself, but at least when I obtained the value, so the combined robustness value here was 4. If I fix this value and run the feasibility problem again, it would generate me a different form of the trajectory that would be closer to the boundary, but the temporal robustness would still be 4. Does it make sense? So the trajectory that you drew still would have.
Right. I was just wondering.
Yeah, the form can change though.
Well, if you use spatial robustness, right, at least you know you're going to, and you maximize it, at least you know you're going to be inside. So therefore you have some magnitude of temporal robustness.
Yes.
Unless the robustness is 0, in that case, you're right on the boundary. But when you do temporal robustness, unless you add some other metric, maybe a combined spatio-temporal robustness value, then you have no guarantee that you're going to be noisy tolerant, right?
With respect to space, yes.
Yes.
Yes, that's one of the issues why this combination would be beneficial. On the other hand, as you said the spatial robustness does go inside, the temporal doesn't. But there is still an issue with the space robustness that is similar to this. With the spatial robustness, even though you go inside, even small perturbations in time would lead to the violation. So in space, it would go inside, but
I don't buy this argument because of continuity, right? There is some continuity. You don't jump. If you were teleporting, I would say yes. But since you have dynamics, as long as you satisfy some dynamical conditions, and you maximize the spatial robustness, by definition, you're going to have a neighborhood that you're also temporally robust.
Yes.
And that's a guarantee. As long as you move into the set and you have non-zero spatial robustness, based on the dynamics, you're going to have some temporal robustness as well.
So let's assume that you have the specification where you need to eventually reach the goal within the next 5 time steps. What might happen is, even if you try to rush there, you might reach only at the 5th time step. And even though you will be robust spatially, so there will be a couple of points later where you are inside the goal set, you might reach this goal set only at the last part of this temporal constraint. That's what I mean by not robust with respect to time.
I understand that, but think the following. If you're 0 robustness spatially, I would buy your argument. But if you are non-zero robustness, then there is a neighborhood for which you're going to satisfy the requirement, even if you have time perturbations.
Yes, correct.
Right. That's the only argument.
Yeah. So I absolutely agree here. And I think that temporal robustness does indeed have this issue with the spatial neighborhood. There are some possible solutions how we could overcome, just like extending maybe the goal sets. But in order to overcome this issue drastically, you do need the combined notion of space and time.
No, I agree. This is fantastic results. I'm just saying, potentially you need to add that combined spatial temporal robustness to make
we
it. We
tried. Not there yet.
Thanks. I can ask more questions, but I guess I can ask some later.
Anybody else asking questions, George?
Yeah, I mean, I'll ask a question about the future more. You presented that the temporal robustness and the semantics, and then you used it in the context of control. That said, one can use the temporal robustness to do things like model checking or monitoring of code that is time critical.
Yes.
And I'm wondering, what do you see as sort of a program that can take us there, where if you want to do some kind of code with concurrency requirements and things like that, to be able to do sort of the robust STL checking of such pieces of code with time critical requirements?
Yeah. So it is possible now, knowing how we can implement the temporal robustness. So I believe that some extension of Estalira tool would be a very interesting direction. And here we will need Georges to help us. But yeah, we have not done any model checking yet or online monitoring with temporal robustness, but it is for sure an interesting possible direction. We had a couple of ideas of how to maybe use temporal robustness for verification of safety constraints. So at Intel, I worked on their responsibility sensitive safety model for autonomous vehicles, where we used spatial robustness to verify how safe their controller is. I know that Jorges worked on implementing the overall complete RSS in STL. So even though we use spatial robustness, it would be actually interesting to use temporal robustness instead of space for this analysis, and maybe perform some online monitoring of those rules, because we have the overall like simulator, Carla, with vehicles running around. So it would be a very interesting application to look at.
Very good. Thank you. I have no further questions.
Other questions from the audience? If not, I think that's a fast exam. So I think George and Georgios, should we have a private session, or can we skip the private session?
We can, I mean, I have no private questions either. So on my part.
Georgios?
We can skip it. This is very, very nice. This is
let me suggest the following. Everybody gets off except the committee. And Arena, you also, and can I send you then a message or something to get on again?
Yeah, it's the